A couple units ago, you were introduced to a type of reaction called a neutralization reaction, in addition to precipitation and redox. But in neutralization, acids and bases reacted together. All you were told was that an acid is something that starts with H, a base is something that ends in OH, and when you mix them together, they make water and salt. And we left it at that. There's more about acids and bases that I want you to know, so we're going to take those neutralization reactions and dedicate an entire unit to them. If you look at the front of your new cheat sheet, you'll see that it's basically a laundry list of characteristics, making this a short and easy lecture. But this is good stuff to make flashcards on and stuff like that, because I can ask you a ton of what should be very simple questions that you'll just want to be able to regurgitate facts about acids and bases. As far as the best chemistry goes, make sure you write everything that I do. The biggest difference chemically that I want you to know about them is acids are made up of hydronium, and he's got a chemical formula of, well, that's an 8, long string breaker, of H3O plus. Bases are chemically made up of hydroxide, which you already knew that from our previous unit, which is OH minus. So in its simplest form, if I have a beaker that's got a solution in it of some kind, but that solution has more H3O than it does OH, it's going to be an acidic solution. But if that solution I'm holding has more OH in it, it'll be more basic. So really, whether or not something is an acid or a base is a battle between these two compounds, whichever it has more of swimming in it. Now you'll notice that we're dealing with O's and H's here. All right, so when you compare that to something like water, which is also made up of O's and H's, you can see why many compounds, or many solutions rather, can be classified as one of these two umbrellas. So we also know that acids are any compound that start with H. And we're going to be naming acids tomorrow in a nomenclature lesson. And we previously learned that bases are compounds that end in OH. So you'll want to have that on the tip of your tongue to answer some very simple questions on your new online assignment. They've got some very general contrast. For example, acids have a sour taste and a sticky feel. Whereas bases have a bitter taste and a slippery feel. Now we won't be allowing you to taste them, so in regards to doing any kind of activity where you're comparing one to another, make sure that you don't put hydrochloric acid in your mouth to see if it's sour. It'll be painfully sour. But again, some general things to compare to each other. Now, based off these characteristics, you can start thinking of examples of acids and bases. For example, name something that you know tastes sour. Okay, Sour Patch. I like that. I like that example. All right, something more organic. Lemons, fruits, right? Anything that has any kind of what you know as being citric acid and things like that. But all of your fruits that usually have a sour taste to them are going to be made up of different types of acids. We don't eat bases very commonly, so you can't easily think of something bitter that you eat. Usually bases are things that you don't want to ingest. But name something that's very slippery to the feel. Something that you might have even used this morning. Did you say butter? I like that. You'd probably use butter this morning. No, butter's not a good example. So, wasn't a bad answer though. Yeah, soap, cleaning products are very commonly bases. So lots of foods are acidic. Lots of cleaning products are basic. A major thing they have in common, you'll notice everything up here right now doesn't match. But both acids and bases are corrosive. Which basically means that they both have the ability to destroy. There's sometimes a misperception that acids are dangerous and bases aren't, where that's not the case at all. Both can be very, very dangerous to the touch, depending on their pH, which will be the characteristic that we end on in a moment. One of the ways that we can tell whether or not an unknown solution is acidic or basic is off of something that's called an indicator. For example, we've got stuff called litmus paper that a lot of y'all did labs with in middle school, where you dip a strip of paper into a solution and see what color it changes. And that'll tell you whether it's acidic or basic. Acids turn litmus paper red. Bases turn litmus paper blue. The same is true for a liquid called universal indicator that will change these colors. But there's a third color that's important, a neutral color. If something's neutral, that means it's neither an acid nor a base, but neutral has a color of, does anybody know? No. No, purple's more bluish. Purple's going to be basic. It's green. It's like the only color of the rainbow y'all missed. As far as indicators go, the color green is a good representation of something that's not acidic and not basic, meaning that it's got the same amount of hydronium as it does hydroxide. Because remember, whether or not something is acidic or basic is just a battle between those two compounds. If there's more of one of them, then that's what the solution will be classified as. Sometimes a solution might have a lot more hydronium than hydroxide, meaning it's very, very acidic, or just a little bit more hydronium than hydroxide, meaning it's only slightly acidic. Or the flip side, a little bit more hydroxide than hydronium, making it slightly basic. We've got a scale that you've heard of that we use to show you how acidic or basic a solution is. It's called the pH scale. And it's a scale that runs from 0 to 14. So what number's right in the middle of my pH scale? What? 7. What this does is it builds two different ranges that you need to be very familiar with. This range from 0 to 7 is the acidic range. So, of course, any pH above 7 is the basic range. Now, based off just knowing that, I could start to ask you questions connecting to the table that we just got done drawing. Consider this question. If I had a substance that had a pH of 4.7, that's the pH that I have in this beaker right here. He's got a pH of 4.7. Would you expect him to have more hydroxide or hydronium ions? Don't answer out loud. Look back at your notes. This solution here with a pH of 4.7, does it have more OH or more H3O floating in him? What's the answer? H3O. There's going to be more hydronium in here than hydroxide, because that's the only way that we would be able to say that he's acidic. Let's look at a different beaker. Let's look at a beaker here that has a pH of 13. If I put a drop of universal indicator into that beaker, what color would you expect it to change? Blue, because bases are blue. Now, as far as those colors go, there's a whole scale of color here. The middle being green. By the way, my 7 here is neutral. So something with a pH of 7 is neither an acid or a base. So we go from green to darker, 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 and then like a bluish purple, and green from like orangish to yellow, or yellowish to orangish to reddish here. So it is kind of a rainbow scale. But you'll want to be able to apply these number ranges of pH to some of these other ideas that we have looked over. Sorry, this would be blue. Now, the further you get away from the 7, the stronger it becomes. For example, if there's just a little bit more hydroxide than hydronium, then we would be in a pH of like 7.5 or 8. But if there's a whole bunch more hydroxide, that's what pushes you closer to the 14. In regards to being corrosive, the things that make the samples more dangerous is the further away you get from 7. Water has a pH of 7. All right? And we all know how dangerous water is. Sulfuric acid has a pH of less than 1. All right, sulfuric acid being one of the most dangerous acids that there is. Something like industrial cleaner, caustic cleaner, all right, has a pH of 14, or right under 14, about 13.8, which means both sulfuric acid and caustic cleaner will burn you if you touch it, because their pHs are so far to the extremes. Whereas something like urine has a pH of 6-ish. All right, for any of y'all that like to pee on yourselves, it doesn't hurt, right? Because even though it's an acid, its pH is close to 7. All right, and that stuff that's close to 7 isn't going to be real harmful. The same as soap. All right, soap has a pH of about 9, hand soap. All right, and of course, they don't sell you soap that burns you. Really gets the dirt off if it burns you. But questions over the pH scale and any of these ideas?